What's going on, y'all? Welcome back. This is Jeff. In this video, we're going to continue our work learning to build and measure circuits. Specifically, we're going to move on to example 7 in our basic concepts in nodal analysis workbook. This example, as you see on screen here, includes a single voltage source and then 3 resistors, 3 1K resistors in series. In order to build this, we're going to need a breadboard. We're also going to need our custom DC voltage source. We're going to need, of course, a battery, and then also 3 1K resistors as seen. Let's go ahead and build this using the instructions in our manual, and then we're going to measure some specific variables. Here we go. As we see in the instructions in our workbook, we're going to disconnect the battery from the DC source. That's already done for us. We're going to connect resistor 1 across B10 and then all the way, it looks like, to I10. And we'll kind of just bend it there for ourselves so that it's right in the middle. And then we're going to go from J10 down to J20 for the second resistor. So now we have resistor 1, resistor 2, and then the third resistor is going to be from B10 to I20. So here we go, B10 to I20. Now I've got those 3 resistors. Next thing I'm going to do is connect the red lead in A10, which is right next to this one, and then the black lead in A20. When I'm ready to measure, I'll go ahead and connect the battery. Let's go ahead and check to make sure that this is indeed what we're looking for. We see a 1-to-1 correspondence here. We have the resistor 1, which is this one in the schematic, resistor 2, which is over here, resistor 3, and we are all good. All right, the next part of this is to make some circuit measurements. So we're going to connect the battery, get our multimeter out, and fill out our table. Let's switch over to that measurement process. Here we are. We're about to connect this battery to make voltage and current measurements, but before we do so, we should define the polarity of our measurement. We have some rules for that process. We said that in a voltage source, we were going to mark the negative and positive polarity of the corresponding voltage drop across that element in the same direction as the connectivity of that voltage source. In this case, we're going to call this V sub V1, since that's the first voltage source. We also know that the current reference direction will always go from positive to negative. I understand completely that the actual current in this circuit goes this way. That just means that this variable will have a negative sign on it. For continuity, for a rule that we're going to use every time, when we assign the current direction, it's always from positive to negative, independent of the actual direction of the current. We're also going to assign the rule that for resistors, we can assign any reference direction. Why don't we go ahead and just assume that the positive goes in the same direction for the first one, so we'll say positive to negative. We'll swap the second one. Let's keep the second one the same direction, positive to negative, and then the third one will actually go in opposite direction. So as we go around this loop, it will go from negative to positive. The point of this is that we don't actually have to know the behavior. This is a relatively simple circuit, and so we can actually completely determine the behavior before we start. But in more complex circuits, when we have, 14, 20, 70, 100, however many elements, these rules will come into play and make a big difference. So we're going to call this the voltage drop across the first resistor. We're going to call this the voltage drop across the second resistor, and we'll call this the voltage drop across the third resistor. We said that the reference current direction will always go from positive to negative. When we look at the current running through resistor 1, that current has the following measurement polarity from positive to negative. Same thing, the current running through resistor 2. And here we've got the current running through resistor 3. Now we have a complete map on how we're going to actually measure the voltage drops across each element and the current running through each element. Let's go ahead and connect our battery and get started with our measurements. We're ready to connect our multimeter. We're going to start with the voltage drop across resistor 1. Looks like we're going to put the black lead on the right side of resistor 1 and the red lead on the left. So here's the first resistor. We take the black lead, put it on the right, take the red lead, put it on the left. Looks like we have a 1.658 volt drop with a positive. So this is positive 1.658 volts across resistor 1. Next thing we're going to do is measure the voltage drop across resistor 2. To do that, we're going to put the black lead on the bottom and the red lead on top. So here I've got the black lead on the bottom and the red lead on top. Whoa, how interesting. 1.658 volts. Finally, we're going to measure the voltage drop across resistor 3 in terms of the resistor. So I'm going to put the black lead on the right and the red lead on the left. So here we go. I can actually attach this black lead anywhere along that node. So I can attach it to that one as well. And it looks like, wow, look at that. Similar but not identical to the last measurement. So here we've got negative 1.653 volts. Final measurement in the entire circuit. Here we've done all of the measurements for one element type. Let's go ahead and finish up with the voltage source. So in the voltage source, I'm going to take the black lead of the black probe or the negative probe, attach it on the bottom, the positive probe, attach it on the top. And here I get 4.96 with a positive. So this is 4.96 volts with a positive. Now we've finished our voltage drops across each element. Let's go ahead and measure the current running through each element. I do want to repeat as a reminder, when I'm going from positive to negative, remember that voltage drop measurements are in parallel, current measurements are in series. So I'm going to have to break the circuit and then put these in series. And when I put them in series, it's going to be like this. The red starts the series and the black ends the series, so that it goes from red to black, and that the actual current will run through the ammeter. So we're going to take our multimeter, put it on ammeter. We'll go ahead and break the circuit. So I'll do the current running through resistor 1 first. Here I break that circuit. It's no longer connected. Looks like I have 1.71 milliamps. 1.71 milliamps, and that's a positive. Next thing I'm going to do is figure out what the current running through resistor 2 is. So I reconnect this circuit. Maybe I'll take the bottom side out in this case. Here I'm going to do in series, so positive on top, negative on bottom. Whoa, isn't that very interesting? Do you notice a pattern? If you were only a few hundred years older, maybe it wouldn't be called Kirchhoff's law. All right, so here we go. We'll do the last one here. So we're going to take this one out. Notice that it is the reverse polarity. So we'll go ahead and take the third resistor out. We'll connect the red lead to the bottom of the voltage source and the black lead to the resistor. And it is in the opposite direction, almost the same magnitude. Check that out. So this is 1.7. Oh, look at. Oh, wait, I guess I should say 70 milliamps. And then the final measurement that we're going to do is the measurement of current running through the voltage source. To do this, why don't we connect it to the top? And it looks like I'm going to have to do black and red. So I'll go ahead and disconnect that part of the voltage source, connect this to the top, and it looks like it's going to be a negative 1.70 milliamps. And this is not a coincidence. The fact that all of these are the same and these elements are in series is actually very much connected to a fundamental principle in circuits. And we're going to come back to this many times, but I wanted to show you that that principle actually shows up in measurements. All right. So now we've got all of our circuit variables, at least the ones we defined previously, but in this example, we actually extend our work in circuit theory. Specifically, we're going to start noticing that the circuit's nodes we can also assign variables to those nodes. Those are called the node potential measurements. Before we get into this, let's go ahead and remind ourselves what the circuit nodes are, and then let's think about specifically what we're measuring when we do that. Remember from our previous video about circuit nodes that the way that we found the nodes of a circuit was to erase each individual element body, and then the nodes were the connected segments of wires. So in this diagram, you see that we've done that. We've taken the bodies of the 4 elements and erased them, and then notice that the connected segment of wires, or the connected leads, we're going to call the individual nodes of our circuit. In order to identify where these nodes are on the actual circuit, I thought it was useful to do this thing where we open up the breadboard. So if you watched my video on breadboards, you remember that we actually took the back off and we took the individual contact strips out of the breadboard. Well, inside this breadboard, so inside this circuit, this is actually what's happening here. We've got the contact strip from A10 to E10, that's this one. We've got the resistor coming out of B10, so that's this one right here. So that metal piece is making an electrical connection with this lead of our resistor. Here we've got our element body, so there's that element body, and then this lead comes down into the contact strip from F10 to J10, so that's this contact strip, and then this lead of the resistor comes up this way. There's the element body, comes down. So when we're looking at identifying where the circuit nodes are, this node right here, node 1, and why don't we just go ahead and label these nodes. So we'll call the blue one node 1, we'll call the green one node 2, we'll call the yellow one node 3, and we'll call the orange one node 4. Remember, those are the connected segments of wires. So imagine for a moment that I took like a pair of scissors. It wouldn't be great with scissors. The truth of the matter is I should do like a pair of wire cutters, and then I cut out each of those bodies. What would be left over is this piece of wire here, so the left side of that resistor, the contact strip underneath, and of course I would have the red wire. The reason I'm not connecting it is these things are a little bit stiff, and it's actually not easy to get those resistors into the contact strips without the plastic casing of the breadboard. But the point is that that node would be all of the wire connected on that side of the first resistor. So it would be this thing, that wire, and that one. Here, the second node would be all wire connected in between resistor 1 and resistor 2. So all of this wire, the contact strip underneath, and then all of this wire. The third node would be the wires between resistor 2 and resistor 3. So all of this wire, the contact strip underneath, and all of this wire. And then the fourth node would be all of the wire between resistor 3 and the voltage source. So everything on this side of the resistor, etc. And you can kind of see how to find those nodes by the inner workings of the breadboard. Now, the interesting thing about this is once we have those connected, we can use this information to say, okay, well, check it out. This is going to be node 1, that's node 2, that's node 3, and that's node 4. And node 1 is literally anywhere along that wire because of the construction of that board. Node 2 is anywhere along this piece of wire on resistor 1 or the top lead of resistor 2. Those are the same piece of wire from the standpoint of electron flow. Same thing down here. Node 3 is anywhere along these two, and then node 4 is anywhere along those. When we're measuring the node voltage potentials, what we're going to do is actually connect the negative lead of our multimeter to one node and then pass the positive lead all along the other nodes. So in this case, I'm going to take my negative lead and attach it to node 4. I am no longer going to touch that lead. So when I leave my negative lead of my multimeter in one place, that's called grounding the circuit. We'll talk a lot more about grounding and about why that makes sense. But for now, what we're going to say is when we measure node voltage potentials, we take our negative lead, leave it in one place, and then what we do is we pass our positive lead to the other node. So if I wanted to know what the node potential for node 1 is, I go ahead and attach my positive lead to node 1, and I get 4.96. So this is going to be a voltage measurement of 4.96. Next thing I'm going to do is take my red lead and move it over to node 2. When I look at the voltage potential at node 2, that's going to be 3.31, let's call it 313. Okay. Next thing I'm going to do is take that and move it down to node 3. Now that's going to be 1.654. And the funny thing is, I could have attached that over to this piece, and look at that. I get the same measurement. That's the claim, that those two pieces of wire are electrically connected. The last thing that I can do is I can actually measure node 4, and you'll notice that that voltage drop should be around 0. There it is. So this is going to be what we call 0.000. The moment that I have done that, the moment that I have a 0 node potential, we call that the ground. So in this case, we're going to call node 4 the ground node. So we have now grounded the circuit. And this gives us a complete representation of the circuit variables we're going to use in this situation. So we've got the voltage drop across each element, we've got the current running through each element, and then we've added a new set of circuit variables, which are the node voltage potentials. In order to measure node voltage potentials, we took the negative lead of our multimeter, attached it to one single node, didn't matter which one we chose, and then we passed the positive lead to all other nodes in the circuit. Anytime we ground our circuit, anytime we attach that negative lead to one of the nodes, that measurement will always be 0. Another way to say that is the grounded node potential is 0 volts. That is the reference node with which we measure all other node potentials. We'll get much more into this later. Just wanted to show that now that we have node potentials in the background, we can do some interesting measurements. Let's move over to why we do this and start building some technology to do mathematical modeling. The next stage of our development is actually to start to understand the wealth of data that we've collected here. There's actually a lot more than meets the eye, like transformers kind of. In our situation, what we're going to do is create a method of describing how this circuit is connected using something called a directed graph, or digraph for short. To do this, we're going to think about each one of the nodes of a circuit as the node of a digraph. Another way to think about this is just draw some dots, vertices or nodes we call those. So this is going to be node 1, node 2, node 3, and node 4. For good form, I think we should definitely label those. So we'll call that node 1, node 2, node 3, and node 4. And then the edges of our digraph, the directed edges, the connections between those nodes, are going to be in the direction of the reference current. So in this situation, because the reference current for resistor 1 goes from 1 to 2, I'm going to draw an edge in that direction. Next thing I'm going to do, from 2 to 3, I'm going to draw an edge in this direction. From 4 to 3, I'm going to draw an edge in that direction, and then we have one from 1 to 4. Just as we enumerated the nodes, we're also going to enumerate the edges. And the way that we're going to do this is we're going to start always by enumerating the edges from the resistors. So we'll start with resistor 1. This is going to be what we call edge 1. Resistor 2 would be edge 2. Resistor 3 would be edge 3. Once we finished all the resistors in our entire circuit, then we move on to voltage sources, and we continue from the last enumeration. We have 3 resistors. The next one we're going to do with voltage sources, so that's got to be edge 4. Using the reference directions for our currents, we construct a directed graph model that completely describes the connectivity of our circuit in terms of the reference directions that we use. Next thing we're going to do is start to investigate a very classic observation between the node potential measurements and the voltage drops across each node that early scientists saw after collecting hundreds or maybe even thousands of data points. I don't want you to worry so much about where this intuition comes from. I guarantee that if you sat in your room for maybe days, months, or years building circuits, making measurements, you would eventually converge on this. But one of the benefits of being a young person in 2020 is that we can use the suffering of people who lived in the past to propel our observations. Specifically, we're going to say that the voltage drop across each element is very much related to the node potentials. In this case, we said that the voltage drop across R1 was going to be 1.658 volts. And we're going to claim that that's actually, in theory, equal to the difference between the node potential at node 1 and node 2. Specifically, we're going to say that it's the difference between U1 and U2. Well, the nice thing is we can check whether or not this is true. We knew that 4.96 minus 3.13, 4.96 minus 3.313, that is 1.647. Those two things are not directly equal, but this is one of the beautiful things about theory and practice. Our measurement instrument on this first measurement was only accurate 2 digits after the decimal place, whereas on the second measurement it was accurate 3 digits on the decimal place, and that's just the internal functioning of our multimeter. But notice that in practice, when we take physical measurements, some of the way that our measurement tools work affect how accurate our chosen model may be. Let's go ahead and check the next one. So we're making the claim that the voltage drop across resistor 2 is going to be the difference between the node potential at node 2 and the node potential at node 3. So that's going to be, in this case, positive gets assigned to node 2, negative gets assigned to node 3. So this would be positive U2 minus U3. Well, we knew that U2 was going to be 3.313, U3 was going to be 1.654. Go ahead and do that on a calculator and you'll get something that looks like that. Those things look a lot closer, and the reason that those measurements correspond a lot more is because we have the same level of accuracy in both measurements. Let's try the next one. We said that the voltage drop across resistor 3, in this case it's going to be positive U4, there's that reference, positive U4 minus U3. So positive U4 minus U3. Well, U4 had 0.000 volts. U3 had negative 1.654. Those are almost identical. They're 1 unit off. And then the last one that we're going to measure is going to be, and in that order, right? So we first did voltage 1, voltage 2, voltage 3, and this one. And that actually, later on, we're going to see that that's very much connected to the way that we enumerated our edges. We'll come back to that. Each edge corresponds with a single branch or single element. Last measurement that we had, we said that the voltage drop across the voltage source was going to be measured at 4.96. In this case, we're going to say that's U1 minus U4. U1 gets a positive, U4 gets a negative, because that's the reference that we put on it. U1 we saw was 4.96, U4 was 0.00. Indeed, those things match exactly. That's pretty amazing. When we collect the voltage drops across each element, we can actually find this information. There is some linear dependence. Get it? Linear dependence. There's some connection between what's happening here and what's happening in the voltage potentials at each node. In fact, we can calculate each of these variables if we know those ones. The last thing we're going to do in this video is take a look at a similar relationship that's happening at the currents in each node. To start making interesting observations about currents, what we're going to do is isolate each node and then look at the currents running out of and into that node individually. Let's go ahead and start with node 1. In node 1, we see that current for resistor 1 is running out in terms of the reference direction. And then for the voltage source 1, it's also running out. We're going to make the claim that the total current running into and out of a node sums to 0. Later we're going to know that as Kirchhoff's current law, but right now what we're going to do is start to observe that in the data that we've collected. In this situation, notice, we're going to say that when a current leaves a node, it gets assigned a positive, and when a current enters a node, it gets assigned a negative. And those are arbitrary rules, but they are rules that work from the convention of building this theory. So every time I see a current leaving, I'm going to put a positive. So in this case, I see in node 1, resistor current 1 gets a positive sign, resistor current 2 gets a negative sign, and we're claiming that those two things should sum to 0. When I actually check the measurements, so resistor current 1 is going to be 1.71 with a positive sign. Resistor current 2, voltage source current 1, or the current running through the voltage source, is going to be negative 1.70. That has a positive sign because it's running out. And when we sum those, indeed we get something very, very close to 0. These are in milliamps, so that's going to be 0.01 milliamps, which is like 10 to the negative 5 amps, which is quite small. Effectively, that's 0. Let's go ahead and check the next one. When we're looking at currents coming out of a node, we look at all currents entering and leaving. If a current enters a node, we put a negative on it. If a current leaves a node, we put a positive on it. So in this case, this equation is going to say negative IR1, because that's moving in, plus IR2, we're going to claim is equal to 0. Let's go ahead and check the data. The current running through resistor 1 is going to be 1.71 amps. We're going to put a negative on that because it's entering node 2. The current running out of node 2, aka the current running through resistor 2, is going to be 1.71. When I add those up, I indeed get exactly 0. Some Russian scientist many, many years ago noticed this, and he called it a current law, Kirchhoff's current law. That's exactly the observation that led to this very, very famous result. If only you had your breadboard and multimeter back in the 1700s, you'd be famous for life. Okay, let's take this thing. When I look at the current running into node 3, that's going to get a negative sign, so negative IR2. And now I have another current running into node 3. That is also going to be assigned to negative. When we look at our data, negative IR2 minus IR3. Minus a minus becomes a positive. This is going to be 0.01, negative 0.01 milliamps, which is negative 10 to the fifth, negative 5 amps, very, very close to 0. And finally, we can go ahead and confirm when I look at node 4. Let's take a look. When I have the current running in, so that thing goes into, we're going to assign a negative sign to that one. The current running through resistor 3 runs out of, we're going to assign a positive sign. We'll go ahead and mark those in this order. So positive IR3, then negative IV1. So IR3, the measurement was a negative. That has a positive sign associated with it. The sign doesn't change. So this is negative 1.70. We're going to go minus IV1, so minus a minus, those two things cancel out, and indeed we have something exactly equal to 0. Think about that for a moment. We know that the voltage drop across each element can be directly calculated from the node voltage potentials at each node, and then we also see that there is an interrelationship, an interdependency between the currents running through each element, which is called Kirchhoff's current law. We're going to introduce that formally later, but I wanted to show you that when we measure current and measure voltages, there's a lot of math and interesting observations. Thus, the act of measurement is actually an act of discovery. I am accelerating this discovery in this video by giving you some observations that might take you months to find for yourself. Later, as we do more measurements, we will be ready to formally state these observations as laws Then once we have those laws, we'll be able to build mathematical models using those observations. But my opinion is it first starts with observed data on real circuits, which is exactly what we've done here. In the next video, we'll go ahead and take a look at a more complex circuit, a 4-element circuit, but instead of doing it in series, we'll do it in parallel. I'll see you in the next video.